Welcome in the second part of our introductory video about process data reconciliation and validation in chemical and power industries. In the previous part, we have talked about kinds of data redundancy. What are reasons for data reconciliation? What is needed for data reconciliation? The important item was the classification of variables. In what follows we will show also mass balance examples solved by the program Recon. If you want to try these examples on your PC, you can download your personal copy of Recon. The free light version is capable of modeling flowsheet of industrial size. The list of topics treated in this video covers main interests of attendees of our data reconciliation courses in the past. Because this is only the introductory video, it will contain only minimum of mathematics. It is focused on understanding basic data reconciliation ideas and benefits of it. Data reconciliation is based on mathematical modeling. Further on we will suppose that the model is formed by a system of nonlinear algebraic equations in the implicit form. In the model are used three kinds of variables, namely measured variables, unmeasured variables, and constants. Such general model comprises typical engineering models like mass and energy or thermodynamic functions. If we collect values of measured variables, in a redundant system the equations will probably not be zeroed. The reason is that measured values are a little bit corrupted by measurement errors. Now we look for the new reconciled value satisfying the model. There are variables x and y with roofs fulfilling exactly the model. We require that with reconciled values the model equations are exactly zeroed, and at the same time the weighted least squares function has its minimum value. The weight coefficients are reciprocals of squares of measurement errors standard deviation sigma. If we suppose that the probability distribution of measurement errors is so-called normal distribution, such solution is identical with so-called maximum likelihood solution. In theory of data reconciliation, we can meet with the generalization of the least squares function containing so-called covariance matrices of measurement errors. This case will be not treated in this introductory video. In the reconciliation software the solution proper is usually done in two steps. The model is decomposed into two parts. In the first step is done the reconciliation of redundant measured variables. In the second step are calculated unmeasured variables from previously reconciled values. There exist various mathematical methods for decomposition of the main model. The same holds also for minimizing the least squares function. The solution for linear models is found in one step. Data reconciliation with nonlinear models requires iterative solution based on some nonlinear programming method. To summarize main features of data reconciliation, we can say that it is the only systematic way how to analyze and implement measurement and data processing in large industrial systems. Data reconciliation and validation should proceed in the following steps: building the mathematical model and analyzing its solvability. Classification of variables as redundant or non-redundant and observable or unobservable. The least squares solution of data reconciliation. Final data analysis and presentation of results. It is clear that for large industrial systems some effective software is essential. Now we will show a simple Recon example. With the light version of Recon is provided more than 30 solved examples. The name of a task starts by M, for mass and component balance, by E, for energy balance, by H, for tasks with hydraulic models, and by U, for user-defined equations. We will select task MC2, which is the single component mass balance with 4 nodes, 6 measured streams and 2 unmeasured streams. In the flowsheet, the measured streams S1 to S6 are drawn as full lines and the unmeasured streams S7 and S8 are dotted lines. We can see that, for example, stream S1 is the measured stream with the measured value 100.1 and its uncertainty is 2% of the measured value. We can now calculate the task. In the results file, we can see the course of iterations and the global data about the task. Then follows the mass flow rates table with streams names types. Types codes are MC for measured corrected, which means reconciled variable, MN for measured non-corrected, which means non-redundant, and NO for non-measured observable. In next 2 columns are input values and reconciled values. In the next column are uncertainties of results denoted as absolute errors. This task has 4 model equations and 2 unknowns. The degree of redundancy is therefore 2. Very important part of data validation is the statistical analysis of data as concerns possible gross errors. We have prepared a small example. We are starting from the data set with no errors. Then we have introduced the gross errors plus 10 tons per hour to the stream number 1. After the data reconciliation, we can see that the original big error was dispersed among almost all flow rates. The exception is the flow rate of the stream S2, which is measured but non-redundant. It is clear that the problem of gross errors is of the key importance. Gross errors treatment is usually done in 3 steps. The first question is whether any gross error is present. This phase is called gross errors detection. If the answer is positive, we should try to find the cause of this issue. We speak about so-called gross errors identification or localization. The third step is removing error data from the input data set. Gross errors elimination problem is well known for a long time. There exist several basic methods with many of its variants. For gross errors detection, there are, for example, global and local tests. For gross errors identification, there are methods of normalized adjustments or the analysis of nodal imbalances. More complicated is the case of multiple gross errors. We can't go here to details. Now follows the reckon example. We load the reckon task MC3. This is the continuation of the previous example MC2. In this case was added the gross error plus 10 tons per hour to the stream S1. After the calculation, the message informs us that a gross error was detected. We can also see that the critical value of the status of data quality, which is 1, was exceeded. There appears also the message about significant nodes imbalances. On the flowsheet there appear also red marks showing suspect measurement streams. The next steps available in Reckon can help to localize the cause of the gross error. To conclude this part about gross errors, we would like to say that the full automation of the whole gross errors elimination process is not possible. The methods for automatic identifying the sources of gross errors are not reliable enough. Therefore, Reckon does not offer the automatic gross errors elimination. It only supports natural intelligence of his user. There are several important benefits of data reconciliation. The first benefit is that reconciled values are consistent with laws of nature. This sounds a little bit academic, but it has important practical consequences. Consistent data can be easily transformed to accounting and financial systems. Reconciled mass accounting represents the major part of data reconciliation systems installations in industry. The second benefit stems from the fact that reconciled data are more precise than the original measured values. In practice, this improvement of precision is in the order of several tens of percents. To achieve such improvement by instrumentation upgrade would be very costly. The importance of gross errors treatment was already mentioned. The other benefit is that by the solution of the complex model many unmeasured variables are computed. Not only unmeasured process variables like flow rates or temperatures, but also important key performance indicators. There is also a group of benefits based on sensitivities of results on values of input variables. The concept of parametric sensitivities can be used, for example, for the analysis of propagation of measurement errors in the process of data reconciliation. This can help to find bottlenecks of results precision, which can be used for instrumentation system improvement. Parametric sensitivities can be also useful in finding variables which significantly influence key performance indicators. This functionality is useful in plant optimization area. Now we will show one simple example. We will again use the simple mass balance flowsheet MC2. After calculating the task, we will select menu Calculate and Propagation of Errors. After selecting the stream S7, we get this table. In the column Share we find the main causes of flow rate S7 variance, which is measure of its uncertainty. This says that 16% of the variance is caused by the uncertainty of flow rate S1, 62% by uncertainty of flow rate S2, etc. This informs us that the flow rate S2 is the bottleneck of S7 precision. This instrument should be carefully maintained. If we need to calculate flow rate S7 with higher precision, we should replace the flow meter S2 by a more precise device. The application of data reconciliation is not without problems. Several possible issues should be watched carefully. The first important problem can be the behavior of a plant in time. In classical balancing, it is supposed that the production process is at a stationary state. Data processing system averages values of fluctuating variables and uses the averages in further data processing. There can be also changing inventories like tanks between process units. Recon is capable of dealing with such cases. We talk about so-called dynamic balancing. We can also meet heat losses to the environment in the case of heat and energy balancing. In some cases, when the equipment is thermally isolated, heat losses can be neglected. In other cases, the heat loss should be estimated and included in the balance. There can be also errors in models. This is usually detected during model tuning when the model insufficiency manifests themselves as an unexplained data error. In modeling systems with complex stoichiometry, it is recommended to model reactions via so-called reactions invariant reactor. This is typical for biotechnology tasks, pharmaceutical production, or so. We can also meet ill-defined species like coal, biomass, or oil. The empirical composition should be updated by chemical analyses. The care should be also given to thermodynamic data like heats of combustion. In this video was presented Recon, the software for mass, components, energy and momentum balancing and thermodynamic modeling with data reconciliation and validation. Recon is generic data reconciliation and validation system which has several forms. The first is the executive program, which can be managed interactively. This is used mostly for model building and tuning. The executive program can be also triggered automatically by a scheduler. This is used in Recon's online service. There exists also the Recon DLL library, which can be incorporated in a third-party software. Recon's value-added features differing it from other data reconciliation and validation software available on the market are: it is the most comprehensive statistical solution, which provides also the power of gross errors detection. It is easy to change it from the data reconciliation and validation mode to the simulation mode based on real process data. This means that it is ready for so-called data-driven simulation. It is accompanied by the complete set of supporting software, and no third-party software products are needed. Recon includes simulation, performance analysis, data mining, and what-if queries modules. The powerful free light version is sufficient for models testing and for academic use. This is only a short note about interesting history of data reconciliation in practice. It was invented independently more than 200 years ago by the trinity of mathematicians from Germany, France, and United States. The first use of it was in exact sciences like astronomy and cartography. Between two wars it was used intensively in cartography for reconciling measured angles in triangulation nets needed for making maps. The first use in industry dates to 1961, when data reconciliation was used for yield accounting in a refinery. Later it was used in balancing of minerals processing, chemical plants and power plants. There are now thousands of data reconciliation and validation applications in chemical and power generation industries. There exist hundreds of papers and several books about data reconciliation and validation applied in process and power industries. A special branch of data reconciliation and validation is the electric energy transfer and distribution. The importance of this area increases with using distributed renewable electricity sources. Probably the first book devoted partially to data reconciliation is Chemical Process Structures and Information Flow by Richard M.R. Next two books came from Chemplant Technology. The first is focused on using data reconciliation in area of process plant performance monitoring. The second book, covering extensively mass and energy balancing in process industries, contains several chapters on data reconciliation, and also the case study about yield accounting with data reconciliation. Next two books are monographs which has data reconciliation directly in their titles. The couple of books by Miguel Bagajewicz contain the last development in this area. The last book, Power System State Estimation, is a sample of literature about data reconciliation applied to electricity distribution networks. Every modern process plant is not possible without instrumentation, control, and data processing system. The significant investment in such system can be devalued by instruments malfunctions and failures. The use of raw data for higher-level activities like advanced control, optimization, etc., can end by the well-known garbage in, garbage out effect. The investment to a data validation system represents only a small fraction of investment in the instrumentation proper. Working with good validated data pays off very soon. This is the end of the introductory data reconciliation and validation video. Thank you for your attention and patience.